Welcome to AP Chemistry. Redox reactions are the last type of chemical system, in addition to gaseous systems, acid-base reactions, precipitate reactions, and aqueous buffer systems, that we will analyze using our understanding of equilibria. A redox reaction includes many types of reactions. All combustion and detonation reactions are redox reactions, in which at its most basic level, electrons are being exchanged between two species. Oxidation, named after oxygen, is the process of losing electrons. This was named because oxygen, being very electronegative, second only to fluorine, is an excellent oxidizing agent, removing electrons from other chemical species. Oxygen in this dynamic, however, would experience the opposite process, that of being reduced. Reduction can be associated with the fact that through gaining electrons, the charge of the reduced species will become reduced. In the example provided, copper solid is being oxidized to form copper-2 ions in solution, and silver ion is becoming reduced to form silver solid. Both processes together form a redox reaction. In order to identify whether or not a redox reaction has occurred in a chemical equation, we need to introduce a new technique, that of determining oxidation numbers in a chemical formula. It is important to note that oxidation numbers are a way of treating all bonds as if they were ionic bonds, with the more electronegative atom winning in each instance of a covalent bond. The oxidation number rules are easy to remember if you focus on the basic three: fluorine, oxygen, and hydrogen. Fluorine is always -1. Oxygen's oxidation number is always -2, except when partially bonded with itself, like in the case of peroxide. And hydrogen is always +1 when bonded with nonmetals, and -1 when bonded with metals. From these three rules, we can work backward to typically find all oxidation states. Take a moment to figure out how each nitrogen atom was determined using the chemical formula to the right. The purpose of assigning oxidation numbers is not only in order to determine whether or not a redox reaction has occurred, but also to determine the specific half reactions that have occurred as well, including oxidation and reduction. Using the half reaction method, we will thus balance each half reaction and determine the moles of electrons that will be exchanged in the entire chemical process. Note the specific steps provided below. Now, in order to obtain energy from the redox process, an electrochemical cell, also called a galvanic or voltaic cell, separates the half reactions into two components in order that the potential energy that would be released from the electron flow can be put to work. The anode compartment in the electrochemical cell is the site of oxidation. Anodos in Greek means the way up, and electrons move up and out of the chemical cell. The cathode compartment in the electrochemical cell is the site of reduction, kathodos in Greek meaning the way down, and electrons move down and into that chemical cell. These half reactions will always match the half reactions that you have balanced using the half reaction method. Cell notation at the bottom is a shorthand way of representing the entire cell, showing the anode electrode first, and then the anode solution, followed by the cathode solution, and the cathode electrode. It is important to note that either a porous disc, or salt bridge, or both, may be used to connect the ion flow in both chemical cells. This is because as the reaction proceeds uninhibited, positive electric charge will build up in the anode and negative electric charge will build up in the cathode. Therefore, oppositely charged ions must be freely able to flow into the respective compartments and negate the buildup of any total electric charge. Gold, silver, and platinum are typically considered noble metals due to their inability to corrode easily. Electrodes made of these elements, most commonly platinum, will be used when there is no solid substance associated with the half reaction. Every half reaction will be associated with a specific reduction potential measured in volts. This voltage is the maximum work that can be done per charge associated with the half reaction. These do not change when multiplied by a certain coefficient. They are constant in their association of the chemical process. Using these half reaction potentials, the potential for the entire chemical process can be determined. Of course, for the anode, the site of oxidation, the voltage will be the reverse value of the reduction potential provided. Every spontaneous electrochemical process will result in a positive electric voltage. Every non-spontaneous electrochemical process will result in a negative voltage. We recall that the maximum amount of work associated with a chemical process is the definition of the change in free energy. Since the maximum amount of work done is equal to negative of the product of electric charge discharged and the electric potential, and since the electric charge is equal to the moles of electrons exchanged times Faraday's constant, which relates the moles of electrons to their specific amount of Coulombic charge, we can simplify this relationship such that change in G is equal to negative NF electromotive potential. This allows us to determine the maximum amount of work in kilojoules that the chemical process can perform. Eventually, the electrochemical cell, or a battery, which is a series of electrochemical cells, will run until the process is complete. That is, when equilibrium is reached, and the process will no longer be active, but dead. Thus, change in G must not only consider standard conditions, but the equilibrium dynamics as well. Bringing together our former relationships at the top, we can create an equation that solves for the real electrochemical potential in volts that the chemical process can perform. Note that this potential incorporates Q, the reaction quotient, and that the longer the process runs, the smaller the actual voltage will be, until it reaches equilibrium, at which point the voltage will be zero. It is important to note that the entire process can be driven in reverse using a power source greater than the voltage of the electrochemical cell. In such an instance, we have the basis of an electrolytic cell. Now, electrochemical cell potential is very similar in analogy to water pressure. In this analogy, we can also incorporate the notion of electric flow. Electric flow is measured in amperage and is the total amount of charge, measured in coulombs, flowing per second. This is the definition of an amp. Electroplating, which uses the setup of an electrolytic cell, plates a layer of metal from a solution to a surface provided using the reversed flow of electrons. Using the relationships previously described, we can stoichiometrically determine the amounts deposited. Till next time we consider the mysteries of the absolute, Crip.